So thank you. I'm delighted to be speaking here on this occasion for Sergio's birthday. I will talk about anomalous diffusivity and regularity for random incompressible flows. I am talking about an elliptic equation, but it's not really that elliptic because most of the interesting part is in the first order term. Okay, so I promise that this is very small. And sort of disappears as we analyze the problem. I'm going to motivate the problem, though. So this is the PDE that will arise. I'm going to motivate the problem kind of from a historical point of view, which involves talking about a stochastic differential equation, which is the Markov process associated to this operator. So this is the PDE, and then associated to the PDE is a Markov process, which is given by this, dxt is 0.2 square root of 2 nu times white noise, or times a Brownian motion, plus a vector field. Okay, so if nu was 0, then this would just be an ODE, but nu is very small, but there, so it's an SPDE. And I'm interested in the case in which this f is random. So in particular, there's two sources of randomness here. There is the f, and there is the trajectories of the Brownian motion. So you can, the way I think of it is you throw some dice and you select the f from the space of all possible f's, and then you have an equation with coefficients and you study it. Okay, and we want to know what is going to happen to the particle here for long times. So we're interested in long time behavior. And from the PDE side, this corresponds to large-scale behavior.
But f is not random at each step.
Sorry?
F is not random at each step. It is.
F is going to be a multifractal, so you will have your randomness accumulating, and it will be homogeneous as a random field. Yeah. Is that what you meant?
At each time t, you.
No, F is frozen. Yeah, sorry. F is frozen. Yeah, it's a frozen vector field. Yeah. Okay, so this model was studied by physicists in the 1980s and 90s. Actually, by some French physicists. Maybe you've heard of them. I think one of them is called Bouchaud, and then there's Bouchaud-Georges. I think they're known. And they studied this when they were in their 20s, I guess, in the late 80s and early 90s, among other people. They break the problem into three cases. The case when f is sort of neither a potential nor a divergence-free field, the case in which it's a potential, and the case in which it's divergence-free. I'm motivated in this talk by the case when f is divergence-free, so it's an incompressible field. Okay, so I'm going to study only that case. The physicists study this problem using renormalization group methods. So they write a 4-page paper with some wiggly Feynman diagrams, and then they write the correct answer down. And so we struggle to figure out how to recover that. Okay, and so it turns out that, so because they're physicists, they just restrict to the case when f is Gaussian. So if you want, you can always just think about the case in which f is Gaussian. That actually helps you, it cannot hurt you. And in that case, the covariances here, the decay of the covariances of your field f, kind of determine its structure. This exponent here tells you how many kind of long wavelengths you have in your frozen vector field. So if the xc parameter is small, then you have longer or more scales, more long-range scales. And if xc is very large, then it's more short-range. Okay, and there's going to be a critical xc at which something interesting can happen. Okay, a special case in dimension 2 is when this xc is also 2. And in that case, your field is your divergence-free field, so it's in 2D, so a divergence-free field corresponds to a stream function. And that stream function will be the Gaussian-free field if you make your f kind of homogeneous. Okay, so that's a very special random field. It's restricted to 2D. Okay, and here are the predictions of the RG derivation of the physicists. If c is bigger than 2, then sort of nothing interesting happens, or at least classical theory applies. You can apply whatever homogenization theory. Your operator here will, on large scales, look like some Laplacian with maybe a slightly larger constant in front of the Laplacian. And the larger constant is because the kind of stirring of the vector field enhances diffusion. Okay? However, if the C starts to become small, then you have more and more and more scales, and you can have a cascade that happens when the parameter crosses 2. So if the C is less than 2, then you should suddenly have super diffusive behavior. So you no longer look like a Laplacian on large scales. In fact, so this thing is, to unpack it, I should have emphasized, there's 2 sources of randomness, so you need 2 expectation symbols. I'm very sorry. So the blackboard bold expectation symbol is with respect to the F. Okay, so this is with respect to the environment or the field. And then once you have selected that, you can look at the boldface, not blackboard bold, thing like this. And this is with respect to the Brownian motion trajectories. Okay, so this like that. Okay, so what we want to know is what happens after you pick the F and you have a typical F. What does the particle do? In case 1, the sort of variance at time t scales like t, like a Brownian motion. And if you have slow decay of these correlations, then the variance at time t can be a power of t bigger than 1. Okay, and this little parameter here, gamma over 2 minus gamma, gamma is this exact number here, okay, according to the predictions of the physicists. And c equals 2 is critical. That's where you cross over between the 2 regimes, and you actually get a square root of a logarithm here. Okay, and I'll explain where that comes from in a second. Okay, so here are the predictions. So there was one set of predictions sort of earlier in the 80s. It actually goes back further into the 70s, but I didn't put everything here. So there are 2 kinds of predictions that you can make. There are predictions that are annealed and predictions that are quenched. This terminology comes from metallurgy. What I mean is that you can fix the vector field and then just look at this expectation. Okay, just after you freeze the vector field, what does the particle typically do? Or you can average over the field and the particle at the same time. So it's like every time you let the Brownian motion run and you do a simulation, you also resample the vector field. Okay, that would be annealed. So there's just a lot of averaging in annealed. And when you measure things with annealed quantities, sort of weird outliers can distort the picture. Okay, so it doesn't tell you about the typical environment. It tells you about the average, the sort of double average. So then there were these papers that came later, and the mathematicians only recently found them, actually, because Pierre Ledouxal was sitting in the room when we gave our first talk on this. And so we rediscovered these papers, and they make sort of the correct predictions. And they make the point that you should think about this model quenchedly. So you should fix the vector field, and then study the trajectories so that you understand what's going on for a typical realization of the vector field, not kind of after averaging. Okay, and that's more physical. They were the ones that wrote down the correct exponent. So actually, the correct exponent is only in the second paper. The first paper predicts the wrong exponent because I think they only did a kind of one-loop Feynman diagram. I don't know what that means, but I think it means that at first order Taylor expansion, their prediction was accurate. And then it was noticed later by some Finnish physicists that they can sort of predict the exact exponent based on that. In any case, you have this exact exponent here of super diffusion. Okay, and then they also argue that in the critical case you had this square root of the logarithm. Okay, so this is the physics picture. How did they make their arguments for all gamma? So the physicists, they really take the case when this parameter that I call gamma, they call it 2 minus xc, so I'm going to write this down. So gamma is 1/2 of 2 minus xc, always. So their arguments are perturbative in gamma. Okay, so they only work when gamma is very, very tiny because they have a big series that they need to converge, and gamma is a small parameter. It's a perturbative RG argument. This is sort of how they always work. You need some smallness coming from somewhere. Gamma, this small parameter, is their smallness. And so their arguments only work for small gamma. And then they say, well, you can do things like plug in gamma equals 4/3, and then you get good formulas. But these are sort of extrapolated. Okay, so they just say our series converges for small gamma, and therefore for all gamma we can predict stuff. Okay, but even at a physics level, we don't have a derivation of super diffusion apart from this sort of perturbative regime. Okay, let's see. So what did they say their motivation was? It's interesting to open there. So they basically wrote a book on it. It's several hundred pages. They didn't just discuss this model, they discussed other models. But yeah, they have a lot of discussion of it. So they say that the point for them is that this diffusion model, xt, for us it's just one particle, but for them it was the distance between two particles that you release in a turbulent fluid at the same time. Okay, so the xt is like the displacement, the position of one particle minus the other. The frozen velocity field is physically realistic on time scales below the eddy turnover time. Okay, so on short time scales, the f is frozen, and they say that that's physically realistic. What did they want to do? They say in the book that they want to derive Richardson's 4/3 law. So what is Richardson's 4/3 law? Okay, just very roughly, it says that if you release two particles, essentially at the same position at time 0, and you measure how far apart they are at time t, the distance between them will be t to the 3/2, typically. The variance will scale like t cubed. Okay, and what you observe is that if you want to model, if you want f to model a turbulent velocity field according to Kolmogorov's theory, then the parameter that you plug in is xc equals 4/3. No, xc equals minus 2/3. This corresponds to gamma is 4/3. Okay, and if you plug that in, then you get that exponent that we wrote down the previous slide becomes t cubed, exactly as Richardson predicted. They go further and say, even if you include the sort of the corrections to Richardson's 4/3 law due to intermittency effects, so you correct the vector field of Kolmogorov to the vector, to something that's more realistic for Kolmogorov-Onsager, then you have a little parameter that you add, and this is the new parameter. And if you plug that in, you get this number, which was already previously predicted a decade earlier by physicists to be the correct exponent for the intermittency corrections to this Richardson law. Okay, so their point, and they go on to say that this is interesting because all of these sort of turbulence laws, even at a physics level, have only been derived by dimensional analysis. And here we at least have a model where we can derive it analytically, at least at the physics level. And so they were happy about that. Okay, so the goal of our work, and I should also say that the work I'm talking about today is all joint work with Ahmed Bou-Rabee, who's at University of Pennsylvania, and Tuomo Kuusi, who's at University of Helsinki. Okay, so our goal is to try to understand this model, to try to rigorously prove some of these things. Okay. By the way, stop me if there's anything unclear. You have questions, of course. Okay. Okay, so maybe, so at this point in the talk, I back up and tell you a little bit about what causes superdiffusion so that you have some idea of what is happening in this model. Okay, so a good way to think about what's happening is that there's going to be a cascade across many scales. Like you set up a bunch of dominoes. The little tiny parameter nu, which I said doesn't really matter, is only there to sort of kick over the first domino, and then all the dominoes fall across all the scales. And so in order to explain how this happens, I need to tell you about how one domino hits another domino, and then we can kind of extrapolate a cascade. Okay, so I want to explain why a diffusion can interact with a vector field and cause a sort of increase in the amount of diffusion that you see. Okay, and I'm going to explain this with a kind of toy picture, which is good for intuition, but not good for anything else. Okay, so don't make too much of the toy picture, but I like it for intuition. So let me explain my little toy picture here. Okay, so I'm going to draw a vector field that's periodic, and the vector field's going to go counterclockwise, sort of on the white checkerboard squares, and clockwise on the black checkerboard squares. Okay, like this. So that along the interface that's continuous and they're kind of lined up. Okay? So the vector field looks like this. I'm not sure how well that shows up. It's difficult to actually draw a vector field. But here it is. This is just a simple cellular flow. I think it's in 2D, so you can just write the stream matrix. It's like sine x1, sine x2 or something. Okay, and you take the grad perp of that, and you get this. So you see that if you're in this cell, you go like this, and if you're in this cell, then you go like this. And then I'm just going to repeat that periodically forever, and then ask myself, what is the particle going to do? Now, I could analyze this from a PDE point of view. The PDE is actually good for the analysis. This is sometimes better for the intuition. So let's think about what the particle will do. Okay. So imagine that you're a particle, and you have a very tiny amount of diffusion nu, and I release you in the center of this little square. Then what you're going to do is there's a little bit of Brownian motion that kind of distorts you, and you eventually start going in these circles, or I guess kind of distorted circles, like this, until you at some point find yourself near the boundary between two cells. And there, if you switch sides, you'll suddenly go in a different direction. You'll go this way instead of this way. And actually, if you're near the boundary of these cells, you can find yourself switching the boundary many times. Oops. You can find yourself switching many times. And you end up, because a Brownian motion will cross a curve many times before it decides which way to stay on. And you'll end up doing kind of a random walk on the edges, just on this sort of skeleton of the lattice. Okay? And so who's responsible for that? Is that the drift or is that the diffusion? The diffusion is responsible for kind of switching which side of the checkerboard you're on, but the drift is the one pushing you around. So there's some sort of interaction between the diffusion and the drift. The diffusion is destabilizing the orbits of the drift, kind of causing chaos. And the drift is taking advantage of that chaos to make you more uncertain about where the particle is going to be, so that the variance is larger. Now, if you zoom out on this picture and look at it from a very large scale, so that these checkerboard squares become very small, then what you'll essentially see is a Brownian motion. The motion of following the edges of the square, this sort of random walk, will be far away dominant above the small diffusivity that you started with. In fact, if you zoom out, the amount of diffusion that you see will go from nu to square root of nu. So you'll have a big sort of upgrade in the amount of diffusion that you see. Meaning that you kind of have a random walk here. If you zoom out, you'll converge to a new Brownian motion, and that new Brownian motion will have this amount of diffusivity. And if we analyze this thing from the PDE point of view, we would see that this periodic problem, by sort of elementary periodic homogenization, will converge to square root of nu times Laplacian. So you'll get a big upgrade in the amount of diffusivity from this. Okay? Now imagine that somehow this picture could be repeated across all the scales. You see some vector field, it increases your diffusion. You zoom out, now you have a new diffusion. If somehow you could erase the old diffusion and erase those scales of the vector field and just remember the effective diffusion, you could maybe play the game again and again over all the scales, and every time you see a new scale, you increase your diffusion. Okay, and you keep doing that until your diffusion diverges as a function of the scale. And having diffusivity that is diverging as a function of the scale is what superdiffusion is. Okay, so for example, diffusion should be, if dr is the diffusion at scale r, then the relation that you should have is that, let's see, so diffusivity is units of space squared over time, right? So it should be that this is the equation. Okay, so if this is diverging, let's say that this is blowing up like r to the gamma. Okay, so then you can solve that equation and work out the relationship between r and t, and it'll be a super diffusive one. You'll have t is r to the 2 minus gamma, and then you put that on the other side, and you have r is t to the 1 over 2 minus gamma, and you square that, and you get exactly the prediction of the physicists. Okay, so this is what's happening, is that the diffusivity as a function of the scale is diverging. Does that make sense? Okay. So I just already preempted this entire slide. Sorry. Okay, so I already also preempted this slide mostly. So I already talked about how annealed predictions have a double expectation, whereas the quenched ones have the variance here. If you have this sort of, just very quickly, if you have this sort of double expectation here for the second moment, you don't actually know that you're super diffusive. it's consistent with a super diffusion, but the second moment can be the big contributor of the second moment can be the first moment squared. So you might have almost no variance, but you may have like for example, if the vector field was always constant but pointing in some random direction, then you would move away from the origin at a linear speed so that your expected position squared would be t squared. So that sounds like a lot of super diffusion, but there's no uncertainty at all about where the particle is. It's just going away at a linear speed. So you can't really distinguish between sort of anomalous drift and anomalous diffusion from a prediction like that. You need that. Okay, so the mathematicians that were studying this problem, they didn't know about this paper of Bouchaud and Georges, and so they thought that indeed this would be true and this would be false. Okay, and the reason they thought that was because you have this random field, and maybe it's the case that your diffusion in really rare environments happens to kind of hitch a ride on a level set of the sort of stream function of your random vector field, and goes for kind of a wild ride and goes far away. But that happens rarely, and maybe those rare events are the things that contribute to this. So in other words, it is the first moment squared. And so this thing was controversial. Okay, so here were the rigorous results previous to our work. So there are several. There's a paper of Ola and Komorowski from like 20 or 25 years ago, which studied the super diffusive case where you have a real exponent. And I shouldn't have used gamma. So they have gamma, but not the right gamma. Here. So they have a kind of two-sided bound. On each side they have super diffusion with like a power of gamma with this double expectation, and the exponents don't match. So it's in some sense it's kind of a crude bound. The problem was later picked up by some probabilists who studied the problem, and again now this is the case gamma equals 0. So you should see a sort of logarithm, square root of a logarithm. And the first result was a two-sided bound that it didn't match, but they had a log over here, and if you believe log goes to infinity, then this is at least super diffusion because it's growing faster than t, because you divide by t and it goes to infinity. And the upper bound is a full log. So later this was improved, so we have the correct square root of log t on both sides, but now we have a double log correction. Finally, there's this paper which removes this double log correction. Okay, and so at the annealed level, up to a constant, they had these second moment bounds which are consistent with super diffusion. Okay, so what happens? No. That ruined my entire punchline, Vlad. How did this? So I have a great birthday cake, but you're supposed to wait. How did it? Okay, I can't. Yeah, I'm just going to use this. The button decided to get stuck. Okay. No, it's here. Okay. All right. So what did we prove? We proved. I'll only use the pointer. So our first result is in the gamma equals 0 case. There we proved, this is now 2 years old, we proved that the variance behaves like a constant, a particular constant times the square root of log t. And the first moment you can have it, or you can throw it out because it's just in the error. Now this is a square root of log, this is a fourth root of log, so we kind of have a quantitative convergence of the sort of variance to the correct constant. And you can have whatever p here you want, so you can have whatever LP moment there. In particular, what's the constant here does not depend on the vector field, and it doesn't depend on the amount of diffusivity that you started with. Okay, so it's kind of universal. So that suggests that this really is the vector field, right, that's doing all the work. It doesn't matter how small nu was, you get the same answer. If you take this constant and you divide out, then you can ask, is there a central limit theorem? Like, do we have actually convergence to a CLT for this thing? I mean, is it converging to Brownian motion? And the answer is yes. If you divide by the correct logarithm, which here it's a time, and here it'll be a kind of a length scale, then you have to do it to the 1/4 because it's a length scale. Then you get convergence to the Brownian motion times the constant. So we proved a limit theorem for the process. Okay, but this is the borderline case though. The borderline case is not as fun as the gamma positive case, which is the case that physicists maybe really care about. So let me tell you about the gamma positive case. So this is work that we're finishing, but it's not the kind of work that we're finishing that will be on the archive next year. It's more like next week. So it's really getting finished. So we're in the gamma positive case, or C less than 2. We need it to be perturbatively small. So we have as long as gamma is less than like 10 power minus 1,000, it's fine. And we have the second moment, and we also have the first moment squared small, so you can have the second moment or the variance. It's just easier to write on the slide, the second moment. So the second moment is equal to a particular constant up to this red error, okay? And the constant is gamma minus 1/2 times the correct power of t. Okay, so we have the power of t predicted by the physicists here, and we have the constant gamma minus 1/2, which they didn't predict, but they almost predicted it because when you let gamma go to 0, the gamma minus 1/2 turns into your square root of log. So if you kind of interpolate between the two results, they did predict it. There is an error here, and this error is not becoming small in any parameter. So it's not going to 0. It's really just a O of gamma 1/2 error. It's there. And this red thing is also random. So this red thing will depend on your vector field. Okay? And the reason is that in the strictly gamma positive case, the largest scale wavelength in your vector field contributes O of 1 amount of effect on your problem. Okay? It doesn't go away. So it doesn't scale away. So because the solutions like the vector field will become kind of multifractal. And so the last 3 scales are not small. And so you do see these errors. But the point is that you see the same amounts of error at every scale. It doesn't go to 0, but it doesn't blow up either. So the whole point is to kind of control this as you change the scale. Okay? And so you see that the whole effect is in the size of gamma. I need gamma to be small because I need this gamma minus 1/2. I need this term. This red term has to be smaller than 1, right? Essentially, for this to make sense. So if the red term starts to compete with the 1, then I lose totally the whole effect. So that's the reason. That's how you see. That's one way to see that this is really perturbative. Okay. This result is uniform in the diffusivity. So you can let nu go to 0, and you still have variance of your process that is that size, independent of nu. Okay. So somehow the variance is not caused by this. It's somehow caused by this. And I emphasize that the variance is also not caused by the fact that f is random. It's not, the randomness is not inherited from f, because here f is frozen. It's true that f is a random field, but you sample it, now it's frozen. After it's frozen, there's still randomness. Okay? You don't know where the particle is going to be, even though this nu is tiny. And it's because of the chaos that's caused at each scale. Okay. All right, so now we can talk about PDEs. Our proofs are not at all probabilistic. That is just for the selling points. If you don't make the introduction probabilistic, then the probabilists don't read the paper, so you have to. But as soon as you go to section 2 and you start setting up your proof, you switch to the PDE immediately. And then they have to read all the PDE arguments. So this is our operator. We don't really care about the process until the very, very end, after the whole analysis is really done. So we care about this operator. Okay? The first thing we're going to do is rewrite the operator, which actually the physicists do as well. This vector field term, the first order term, is antisymmetric, right? But it's useful to write it in divergence form. So you still want to write it like there's a matrix. So we're going to take the operator, and we're going to write it like this: divergence nu identity plus k of it. Okay? And the point is the k is containing the vector field. And for us, the K is the fundamental object, not the F. Okay, so this is an antisymmetric matrix field. Has to be antisymmetric because how else could it encode a first order term? And the point is that, okay, in 2D, this K, because it's antisymmetric, is essentially a scalar times the matrix 0, 1, minus 1, 0. Right? There's only one antisymmetric matrix in 2D. In 3D, there will be 3 degrees of freedom. In this K, and you can identify it with a vector field, and then you would be taking the curl of that vector field. Right? So I'm just writing a divergence-free field first as the grad perp of a scalar in 2D, then as the, what do you call that? A nobile cross curl of a vector field in 3D. But in NED, you can do the same thing. You should just write it as an antisymmetric field. I don't know what forms are. So I think you're supposed to say something about a 2 form, but I don't know what that is, so I'm not going to say.
Is this the Helmholtz solution, or there's more than one solution.
Yeah, I know, but you want this field to be stationary, and that kind of enforces that you're going to invert the Laplacian. The correct way to do it is this. Up to a sign. So I don't know the sign, but something like this. That's the correct way to find the matrix, up to a sign. Yeah. For me, of course, the K is the fundamental thing, and the F is derived from the K. So our assumptions are about the K. We throw the F away once we're done with the introduction. Okay? And the point is that the covariance assumption on the F should be written in terms of the K. And it just says that K is a, if you want to keep it Gaussian, but so it's a random field with Hurst exponent positive. Now, what does that mean? With Hurst exponent gamma positive. Okay, so gamma is the Hurst exponent. So if you don't know what a Hurst exponent is, I don't really know it either, but if you look in 1D and you look at Brownian motion and you kind of let Brownian motion go on both sides to plus and minus infinity, so that you have a kind of 1D curve, or like a 1D random function, that will have Hurst exponent 1/2. Okay, because it's Holder 1/2. So, or almost Holder 1/2. So this will be approximately Holder with exponent positive. So it's a continuous field. It's not going to be Holder exactly with gamma, but anything less than gamma. And so it's going to be kind of a crazy field. Now when I write it like this, to get F out, right, you have to take the sort of row divergence of the K. So the F is going to be in C gamma minus 1. So F is not really a function. And that's one of the reasons for writing K, is that F is not really a function. Now, in this model, because you have this small parameter here, you can go ahead and take your K and your F and you can mollify it or whatever on the Kolmogorov scale, the small scale where nu dominates, and then it's smooth. So you can think of it like that if you want. I don't really care either way. For me, I'm happy to have the K be irregular. But yeah.
So K is irregular, right?
Yeah.
And let's say for this kind of things, since you mentioned that chaos is a very important property, you need somehow that you have a minimal, say, non-regularity. And usually in functional spaces, you say that the regularity is at least something. Here you need somehow the regularity to be at most something.
Yes. So I need the regularity of F to be not Lipschitz. So I need the regularity of K so I need this to be less than 2. But fortunately, I'm very far from 2. I'm like 10 to the minus 1,000. Yeah. So like if F were, so the fluid case, the physical case, did I write it somewhere? It's 4/3. So this corresponds to 4/3. That corresponds to the case where K is C1 1/3 almost. Now, when you take its row divergence, you get F is C 1/3 almost. That's the Kolmogorov's case, right? I think someone.
What I say is that in this class, C 1/3 or C 1/3, you get also a function which are C infinity, right?
No, but this will, with probability 0, be differentiable at any point. Yeah.
Okay, so
I'm not proving this for a whole class. I'm proving it for a canonical ensemble, like the physicists would do, right? I'm not proving it for every possible. Yeah. I've got a specific canonical ensemble. There's a probability measure that tells me my field. With probability 0, will it be twice differentiable at any point? Yeah. Okay. So Hurst exponent gamma means that, where did I say? Yeah, so roughly speaking, the oscillation of k in a ball of radius r is r to the gamma. Okay? Now, when you have a field like this, like a Brownian motion in 1D that goes off, it's really only defined up to an additive constant. Because, I mean, think about if you tried to make a Brownian motion, sort of a double-sided Brownian motion in 1D stationary, you can't, because its oscillation is blowing up. So how do you, I mean, if you try to sort of divide by the, sort of subtract the mean in the ball of radius r and let r go to infinity, it's not going to converge. Okay, so you can't do that. So it's just not meaningful to talk about the value of k at a point. You can only talk about the difference of k at 2 points, or the gradients of k, or something like that. But the whole operator is only defined up to adding a constant skew-symmetric matrix. It doesn't, you kind of can't know what skew-symmetric matrix you've added there. Fortunately, the addition or subtraction of a constant skew-symmetric matrix does not change the operator at all, because I'm taking because if you add a constant, then this goes through, and this becomes symmetric, and you have a anti-symmetric contracting against a symmetric, and it vanishes. So this operator will not care about that. We have the symmetry to kind of deal with that. Okay? So anytime you want to understand what this operator is doing, you're allowed to, when you set the problem up, say you're solving a problem in a big ball, you're allowed to subtract whatever constant from k you want, as long as you do it once. It won't change anything, and you can solve your problem in that ball. So you always subtract the average of k in the ball of radius r, and that leaves the size of k to be r to the gamma, which means that the size of this is blowing up as a function of the scale. Okay, now if you're an elliptic person, you should be very afraid that's very bad, because it means ellipticity is blowing up very fast as a function of the scale. This is a very small number, and you're basically dead. Okay? And if you're going to prove any theorem of the kind that we want to prove, you have to use elliptic estimates. And you can't, because this is just, everything's destroyed. There's no estimate that works. Okay. Anyway, this is we're still going to do it. So here's more precisely what I need to assume about my k. I don't actually need to assume it's a Gaussian field with a Hurst exponent with covariances that decay, like blah, blah, blah. What I really need is this. And I think as a PDE person, this kind of makes sense. I need to decompose my k into scales. I'm going to write my k as a sum of waves. And those waves each have a characteristic length scale and a characteristic amplitude. Okay, so the point is this. K is an infinite sum formally. This part of the sum will not be summable unless you kind of subtract constants, like I said. So don't let that bother you. The point is that every one of these wavelengths has each one of these j's is a random field. It lives on scale 3 to the n. I mean that its smoothness scale is 3 to the n. If you take a derivative, you'll get a 3 to the minus n popping out. If you take 20 derivatives, you get 3 to the minus 20 n popping out. And it's a finite range of dependent field where the range of dependence is 3 to the n. Okay? The typical size of it is 3 to the gamma n. Okay? Now if you write this down just under those assumptions and you compute the covariance of this and then take its divergence or whatever, possibly in the other order, then you will get that the covariances decay like this exponent c here, where they satisfy that relation. So but for me, the covariance decay is neither here nor there. I really want this sort of scale decomposition. In this kind of scale decomposition, I, by the way, need the j's to be independent of each other. Otherwise, nothing works, of course. So I need the noises at every scale to be independent. This kind of scale decomposition is a very natural thing when you are thinking from the point of view of renormalization group. Okay. All right, so what does our main result say? Our main result says that if you look at a cube of size 3 to the m, so you're looking at a big cube, the length scale is 3 to the m, then this operator will be very, very close to a multiple of the Laplacian, notwithstanding all the other stuff that I said, where the multiple of Laplacian is this number. Okay, now I could have written this with the Japanese bracket. I know that I should have done that, but to keep in the spirit of the conference, I could have pulled the nu outside. Anyway, the point is that on scales below the sort of Kolmogorov scale, It's just new, as you'd expect. There's no enhancement to any diffusion because the sort of molecular diffusion wins. And on really large scales, you have exactly the sort of growth of diffusion like a power that the physicists say. Okay? And there's a crossover between them. And the point is the crossover curve is exactly that up to next order. I mean, this is sort of if you write it like this, it's like you have a corner, but the real crossover curve is sort of smooth and it's given by that. So this is more precise. Okay? So that's what it says. Notice that when in this squiggly thing, I'm not saying that there's any convergence. This operator does not converge to this multiple of the Laplacian in that cube. The squiggly will hide in a relative error of size gamma 1/2 up to logs. Okay, so there's a relative error here, but it's small. So you're almost harmonic at every scale. The almost never goes to 0. It's just this. You see the same at every scale. It's a fractal. So here's the more formal theorem, theorem 1. Okay, so there's at every scale, so this m is an integer. It just means that's my scale, that's log of the scale, log base 3 of the scale. So for every scale, there's a random variable. That random variable, I have all the moments bounded of that random variable. They're all gamma 1/2. Okay, you have to pay a price to have a higher moment. And you can have all the moments up to some really large number, which also depends on gamma. And this is you stop there because of intermittency. That's actually sharp. Okay. Now the right-hand side I have to make smooth, but I make it smooth underneath the divergence sign, and I should not have used f. It's very confusing. This f is a given data. It's no longer the f that I had over here. I'm sorry. I forgot to change it to g. But this is a data. The data is c minus 1/2 because I have it under a divergence. Okay. And I want the g on the boundary to be a bit smoother. And then I know that if I solve these two different problems, then in L infinity they're close. And I know that their energy densities are close in the negative Sobolev norm. Okay? In particular, if you integrate this thing and you integrate this thing, they'll be almost the same number. That implies that this thing integrated does not go to 0. Okay? It's anomalous diffusion in the sense of a fluid person would say. Okay? But moreover, I don't just have that the integral is the same as that. I have that these fields are close in the negative Sobolev norm. Okay? And now all this stuff, because I have a big cube here, you have to scale all your norms appropriately. This thing, just take m. I should have just written it for m equals 0. Just take m equals 0 and send u to 0, and you see the correct theorem. All the powers of m disappear, and this is so you have the error here, the error in the energy densities, bounded by random defect here times data stuff. Okay, so it's small. Yeah.
I'm sorry, I just missed something. So you prove that for every k, you can find some s tilde such that blah blah blah.
K is a random field.
Yeah, it's random.
Okay, and this E is the law of that K. Okay.
And the S is for each K you can construct a S such that blah blah. Sm.
Oh, this thing. E, M?
No, the Sm in the...
Oh, the Sm is deterministic. It does not depend on K. Okay? So this is a deterministic, it's found by sort of integrating the RG flow. If I have time, I'll explain. And this is the random defect of the operator from that flow. This is determined by K, but we have bounds on its size. This is totally deterministic and is found by sort of integrating the sort of deterministic sort of average that you expect. Okay? We have a second statement, which is about anomalous regularization. So this operator is very bad. You can't expect any elliptic regularity to hold, especially on large scales. You zoom out, you don't see this, and you have a first order equation. So you should assume that there's no elliptic regularity. Even if the coefficients were very nice and bounded, the best that you would get, say if you applied de-Giorgi-Nash-Moser, is Holder continuity with a small exponent, tiny. We actually do better than you would get from de-Giorgi for a bounded coefficient field. We can prove that the solutions are essentially or almost Lipschitz. They're not quite Lipschitz, they can't be, because if they were Lipschitz, you would have no anomalous diffusion. Because on the previous slide, this thing just doesn't work very well. On the previous slide, I said that this number here is going to something of order 1, And this nu could be going to 0, so this thing should be blowing up. So you kind of can't be Lipschitz and have this be true. But we proved that your holder with exponent 1 minus c square root of gamma. Okay? And this is related to the predictions of Abukov and Corson. The solutions of this scalar equation are more regular than you'd expect, not in spite of the randomness, but because of the randomness. Okay? What happens is the randomness is lifting up the effective diffusion of the equation, and it's that effective diffusion which is regularizing. So you don't get the regularity from the small parameter, you get the regularity from the effective parameter, which is increasing, and it's increasing so fast that it's regularizing your equation. So if our last slide was about sort of anomalous diffusion, this is sort of giving you a bound on how bad, how much of a fractal your thing can look like. It's giving you I guess a bound on the, actually, did I write that? I meant to say that it gives you a bound on the Hausdorff codimension of like the fractal, but I'll come back to that. So here's the exact statement. Okay, sorry, it's kind of hard to state this. The picture is this: if you're standing at scale m, so this is the cube of size 3 to the m. Okay, what you want to do is look at a point in there, and you can choose this uniformly. And you want to kind of zoom in on this point by looking at smaller and smaller cubes. We use cubes, not balls, but it's the same picture. You want to zoom in on that point. And at a certain point of zooming, your energy density will behave like, just ignore this term, like imagine that the right-hand side is 0 now. And this underline here denotes I put a slash in my integral. Okay, so I've done the volume normalization of this. If you were Lipschitz, then this would be bounded by this. That's what you have for harmonic functions. This is saying that it only blows up like this power, which is essentially the Campanato characterization of the Holder space. So it's saying the energy density blows up at a very controlled rate. This 1 minus alpha is a very small number, because remember the alpha can be almost 1 minus c gamma 1/2. So this exponent is like gamma 1/2. So it's giving you a bound on how much the energy can blow up as you zoom in, and that is regularity. Okay? Now, the number of scales you have to go down from m to this smaller scale n is a random thing. Okay? That depends on k. So this is a random variable. It depends on the k. But the probability that you have to skip many scales is controlled. Okay? And this bound should be sharp. Like this is a sharp bound. So you can have weird events. The k can do weird things and cause you to have to skip a certain number of scales, because those scales are bad. You don't have your regularity iteration working there. Okay, but after you have skipped a certain number of bad scales, eventually the scales have to be good, because you have a fractal, and your fractal does not, the correct quantities to study are scale local, and and you have sort of independence between scales, and this allows you to, the bad cubes cannot be correlated across many scales. There cannot be a conspiracy across many scales. Okay, so here are some open problems that we don't yet announce, but there are things which we think that our proofs will give. We just have to write another, we have to write the proofs, which is not fun, but you may ask, in the gamma equals 0 case, you proved a CLT. You proved that not only do you have this superdiffusion, but you have convergence to a Brownian motion of your process, and you have convergence to Laplacian in some sense. What do you have for gamma positive? For gamma positive, you cannot have a scaling limit in the sense that you look at larger and larger scales and you get some sort of deterministic limit. That doesn't happen because of the fact that it's a multifractal. It can happen. However, what should be the case is that you should let nu go to 0 and get that this operator has some kind of limit. Or alternatively, you send nu to 0 and get that the Brownian, the stochastic process has a limit. This is what Christoph Goetzky would call spontaneous stochasticity. That somehow, even though nu goes to 0, as nu goes to 0, this thing should be a deterministic, it's erased, no, here. As nu goes to 0, this should be a deterministic ODE. But if you put a little bit of diffusivity in and send it to 0, in the limit you still get a stochastic process with a non-vanishing variance. Okay, we have proven the non-vanishing variance, and the sort of tightness of that process, but to get a limit for that process, we sort of have to, write another 80 pages of proof or something. Okay, and it's equivalent to showing that this operator in some sense has a limit as nu goes to 0. It'll be a weird operator. The domain of this operator will not include any smooth functions, because it'll be the generator of this very weird stochastic process. And so the domain will have you can't evaluate it on a smooth function. It'll be a weird object, but it's like we're giving a meaning to an elliptic operator with a weird sort of multiplicative chaos-like thing inside. Okay, a second question is about intermittency. There's lots of ways you can talk about intermittency, and I get confused, so I just try to think about this simple case. We solve this elliptic equation. We put affine boundary data. So we solve the elliptic equation in a box with affine data, given unit slope. Okay, so here's the sort of affine. Our solution will have some crazy wiggles, and we want to know what is the approximate LP. Oh, I forgot. No, I miscorrect what I wrote. Yeah, we want to know what is the approximate LP norm of the gradient to the power p. Okay, I put a slash here, so it's the average. If p is 2, we already know what it is. When p is 2, it's this thing without this k, and when p is 2, this k becomes 1. Okay? Now, if you change the p, you should actually change the exponent here. Okay? And that's what intermittency means. And there's a back of the envelope calculation that you can do. I don't think the physicists wrote this, but I was able to figure this out, so it's not that hard. If you let p it should be quadratic, and p is the point. And if you were to take the Legendre differential transform of this, you would get what they call the multifractal spectrum. For those that are interested, I don't know what that means, but you get the multifractal spectrum of the problem. Okay. So we sort of have we have a convincing proof sketch of this. This should not be hard. The one up there is probably going to take a while to write down. Okay. The Green's function, just in case you're interested, should look like this, which I think is funny. This is a little messy, but if you set gamma equal to 0, then this is 3 to the m squared over t. Oh, I didn't write. I forgot to substitute. Sorry, the 3 to the m should be the norm of x. I forgot to substitute. Anyway, so this 3 to the m so x is of size 3 to the m. So this is x. X to this power, if gamma was 0, then this would be squared, and this would be t, and you'd have your Gaussian back. But with gamma positive, you have a weird non-Gaussian shape that's changed with some thin tails. Okay. I promised I wouldn't go over, but I'm now to the proof strategy point, so now I'll start to go fast, even though this is the fun part. How does our proof work? As I tried to convince you earlier with the heuristics, we have to do an induction going up the scales. Okay, there's only one way you're going to prove this. It's with an induction going up the scales. There's no other way. If you think there's another way, there's not another way. Because there's no way to communicate. I mean, you really have to set up the dominoes and let the nu knock over the first domino. And if you're going to prove an induction in the scales, then you need to kind of make an induction hypothesis, which is not too strong, because you have to prove back your induction hypothesis. And so you don't want to set up the target to be too hard. And you don't want it to be too weak either, because if it's too weak, you kind of can't get started in the proof. So you have to make just the right induction hypothesis so that it will really buckle across all the scales. And it's very easy to make to convince yourself there's an argument that will work for the first 6 iterations of the induction before you lose control. But you actually have to get control all the way out, and that's what's hard. So that we call closure. But anyway, the thing is set up to be a renormalization group argument. We need to keep track of scale local quantities. So you can't look at the solution at small scales. You can only look at the solution kind of at the scales you have. And the RG state variables, or the things you keep track of, are this running diffusivity S bar M. The bar means it's deterministic, so there's no randomness here. And then this random defect, which kind of quantifies how well you're close to that. Okay, this is very vague, I'm sorry, but the details here are kind of a bit heavy. The proof shows, the sort of main induction loop shows that this defect remains of this order. And because it remains of that order, you kind of are always in a kind of like perturbative regime where you can compute stuff. In particular, you can compute what happens to the S bar. And so you can continue. Okay, maybe I wrote a slide with slightly more details. There are the two big problems, or there's like 20 problems, but two of the big problems are you can't use nu for anything. And when you're doing proofs of this kind, you want to do energy estimates and stuff. And if you can, and when you do the energy estimate, the non-symmetric matrix, sorry, the anti-symmetric matrix will be killed in the energy estimate, and you'll only be left with nu. That means you're not allowed to do any energy estimates naively at all ever. You have to somehow come up with a whole theory of coarse-graining this equation. So we sort of developed a theory of coarse-graining equations like this, which allow us to do sort of energy estimates renormalized in some sense. Okay? And the second problem I already talked about, it's that it's hard to come up with the correct induction packet so that you can get, so that it'll sort of prove itself. Okay? But our sort of coarse-graining theory, we managed to package them in a way that kind of reproduces itself as you go up the scales. I try to give some idea on this slide about how it works. What we do is we take the space. This is very much like an RG proof. We take a big box, we chop it into small boxes. And we don't just chop it into one set of small boxes, we chop it into all possible sets of triadic sub-boxes. And in every single box, we try to understand what the diffusivity is by studying a finite list of problems. Okay, we sort of study, you give it certain boundary data, and then what does the solution do, and what does the flux do, and so on. And so we have a finite list of sort of response problems that we sample. When you're doing these, one of the problems is that a diffusivity is not a physically it's not something that you can observe, right? You can't measure diffusivity, you have to infer it. So you can't. What that means for us is that we're not just going to average something over the box. We have to kind of discover it by solving little PDE problems in every box, stitch them all together into one random variable, and hopefully that random variable has enough information that we can continue the argument. Okay, so it took sort of years to build this theory. And then how does the argument work in brief? The idea is that we want to gradually, as we zoom out on the problem and look at a larger scale, somehow sort of integrate out the smaller scales. And the way that we do it is we take the operator in some box and we chop and we throw away all the scales on boxes larger than that. So we just cut off the k and throw it away. And then we zoom out on this box, and because we have no more scales above that scale, we essentially homogenize it. It goes to a Laplacian. So we see a contraction in the air. So that's the contraction step. If you throw away the bad scales, the sort of larger scales, they're not in your way anymore, and you see a contraction. But then we have to put the scales back because it was cheating to cut the scales off. So now we put them back. And when you put them back, you pay a price. And this is a difficult procedure because when you put the scales back, you have to do essentially an energy estimate to measure the difference between the two solutions, one with the scales and one without the scales. And if you do the energy estimate, you have the small nu here, which you can't use. And so you have to have a kind of coarse graining of the sensitivity estimates, okay? And that's step 2. So you can delete the scales, homogenize, put the scales back. And then we have, because we have to holder away bad events, the stochastic integrability, or the moments that we're using in the induction loop, deteriorate, which means that our proof without this step would work for like 13 steps of the induction and stop. So we have to do some procedure where we show that our coarse graining is in fact insensitive to bad cubes. So we just sort of, it's more insensitive, there's a kind of noise insensitivity. And so we do that. There's some technical argument which does that. And you put these 3 together, and then the induction packet for the random defect propagates. And then once you know that the random defect is small, you kind of solve a perturbative problem to compute the next S bar. And the sort of recurrence relation is this. And when you integrate this curve, this is essentially in ODE, and it's the sort of renormalization group flow equation, and you integrate it, and you can find that it solves this formula, which is I haven't written, but it gives you the correct formula. Okay, so that is how it works. Okay, so I have a slide about how you prove anomalous regularization. Maybe I will skip it. because I'm running out of time. Now I talk about all the previous works, which I don't have time to mention now. Okay. But I have a birthday cake, so thank you, sir. I was up late. I drew this by hand.
75.
There's exactly 75. There may be one or two that have already gone beyond the event horizon, but I think before they did, there were 75.
So, further questions? Well, it's very impressive. So, what are the next steps?
What are the next steps?
Obviously, we want to go to.
Well, so some of the next steps I wrote. I'd like to prove the intermittency and things like that. I would like the parameter gamma to be larger. So there is some hope that we could find a way to do some non-perturbative, because the fluid is really this one, or even bigger. But that's a problem even at the level of physics, I think. I would like to take this set of techniques and apply it to field theory, because I think that some of the same issues you have in field theory you have here, where you do have to renormalize something that is essentially a diffusivity. And so these techniques should apply, I think.
So in spontaneous stochasticity, the idea is really to define a solution of the equation X equal F dt. And this regularization is just a way to define this kind of stochastic object. And in particular, what they assume or what they expect is that it does not depend really on the way you regularize. So if you replace mu Laplacian by mu times any diffusive term, you expect to get the same.
You'll need it to be isotropic, because if you mess up isotropy, things get crazy. So I didn't say this enough, but my F needs to be isotropic. If you start making it anisotropic, it's not going to do this. You'll really have like the diffusivity in the x direction and y direction will start growing at different powers. It'll become crazy. So you do need to, however you regularize it, should not, you can't sort of regularize with an anisotropic Laplacian, but you can regularize, yes, you can regularize essentially with anything. Our proof will show that this will be Cauchy and nu. And then if you want to come up with some other regularization, you can probably, based on that, show it's the same.
Because it could not be something like an elliptic operator with non-constant coefficient, because then it would not be.
It can, yeah. Okay. Let me think about that. So you could have, as long as it's scalar and smooth, it's fine. So as long as you have something like A of x identity, where A of x is scalar, that should be fine, I think, as long as this is smooth. If this has all kinds of scales, then you're in deep trouble, and it'll interact with the other thing. But as long as this is smooth, it's fine. If you start making this be a matrix with different eigenvalues, then it's not. I don't think it'll be true.
You think it's not?
Yeah, I think it's not true. Yeah, and it goes to the. If you start doing an anisotropic vector field, the result should not be the same. Because if this would be anisotropic, but f is isotropic, you can switch and switch variables and make the f be anisotropic, and then you won't have the result. Yeah.
I just want to ask a philosophical question. How come, or why do you think these physics prediction based on IID random scales piling up on top of each other and the prediction from fluid mechanics, why do they match? There's nothing random. You shouldn't need quantum mechanics to simulate the flow past the ball, right? So there's nothing random there, and yet they match. Is there any understanding of why that's so?
You have a fluid equation, which means you have a Laplacian, right? Your Laplacian is only there because something on a smaller scale is really random. No randomness, no Laplacian.
But you don't have randomness in F. That's the one.
Right. Yes.
That's the one.
Yes. So Why is there randomness in the F? Why is that a good model?
Why do they seem to match? Because they do seem to match. And that's a miracle, which I just don't understand.
I mean, philosophically, I mean, if you want me to say something total BS, philosophically, things want to behave like they're random even when they're not. I mean, the prime numbers look like they're random. I mean, right? I don't know. It's like you have to have a really good reason for something to not look like it's random, which is why these random models are so good, I think.
But I thought that the randomness was generated from the viscosity, but the viscosity is very small. Right?
Yes, yeah, that's right. The viscosity is like a little fire that starts it's like a match that starts a forest fire in the scale. Yeah. It has to be there. If it's not there, you can't even. I mean, if you don't have this thing, then this ODE doesn't actually make sense because this doesn't have the regularity to make sense, right? And I don't think the answer is find the solution theory for this ODE. That's not the answer. The answer is this is actually the thing that makes sense. And then you send to 0. Yeah.
So, excellent starting point for the tea break.
Thank you.